Was it a great session?
Okay, cool. I'm going to get started. So hopefully we finish by 7:30ish. Okay, so this presentation is entitled Measuring Intelligence, a Tour. We're going to look over a lot of key developments in thought across history of how people have tried to measure the very vague concept of intelligence, as has shown in previous conversation about trees and humans. Talking about intelligence is kind of hard. And so I hope this presentation is maybe a good formalization of how we might be able to talk about intelligence. Okay, so we're going to talk about the following works. First, the classic by Alan Turing in 1950, Computing Machinery Intelligence. That's where he introduces the original Turing test as it's popularized now. Second one is by John McCarthy in 1979. The paper Ascribing Mental Qualities to Machines. As is tradition now, introduced by Yegor, I'm talking about a Sigmovic paper. I thought it was funny, completely unrelated. Then we'll move on to sort of the main work here, which is by Francois Chollet, the creator of Keras, and also main contributor to the TensorFlow framework, entitled On the Measure of Intelligence. So that was very recent, that's in 2017. So that's like a very modern conception of how we might measure intelligence, especially in context of recent advancements like deep learning. And lastly, we'll talk about the abstraction and reasoning corpus, or the ARC challenge, which was also introduced in 2017 by Chollet. These two are tied together. ARC is a very interesting problem. It's like the sort of the modern random problem for intelligence to solve, which will be cool to look at as well. Okay, so some brief things on what's ahead. Turing talks a lot about arguments for machine intelligence, and also his work is interesting to think about from a historical perspective. He's coming at a time where computing is sort of very recent development. McCarthy is giving us a framework to talk about human qualities in relation to machines and programs. So what does it mean to say that, let's say, a machine is conscious, or that it's thinking, or that has beliefs, right? So McCarthy is giving us a philosophical framework to think about that. And then Chollet, his paper does a lot, but I think what's most interesting is that he actually gives us the concrete equation for the intelligence of the system, which is very big, and we're going to try to understand that as well. And then also ARC is a concrete data set or task from which we can try to optimize intelligence that Chollet also proposes, as well as many other cool things. Okay, exciting news. Why should you care about this? Hopefully you already care about it because it's cool. But also, Francois Chollet, creator of Keras and principal contributor to TensorFlow, will be coming to have an in-person Q&A at DDUG during finals week. He's coming over, you can shake his hand, get his autograph, whatever. Yeah, that'll be cool. So hopefully y'all get a sense for what his paper is going to look like and talk about. Q&A, we can also talk about other things as well. It's also a good time to briefly talk about our other, the rest of our quarter. We have some pretty cool guest speakers lined up. Next week's JC, Alec will talk about AI ethics. Week 9, we have my Marxism professor, Alice Weidbaum, coming to have a discussion with us. We're going to be reading, well, looking at a Black Mirror episode, probably, and discussing that, which will be cool. Week 10, Chayton has snagged his ML professor, Kevin Vanderson.
Yes, I nagged him this morning again, and he said he will respond to me. So that was like, in a week, I'll give an email about the date.
So, right. So week 10, hopefully we'll have him as well. And of course, French locally coming in finals week as well. So that'll be a nice close to this week.
And we have Alec.
I said that.
Next week. Yeah. Oh.
Good to reiterate. Yeah. most important. Okay, let's start it off. Okay, first paper, Computing Machinery and Intelligence by Alan Turing, written in 1950. This is like a huge paper in terms of thinking philosophically and concretely about intelligence of machines. Here are some of his key contributions, right? So he's principally concerned with this question, can machines think? So his first statement is that that question should not be answered on the basis of democracy or intuition. So we shouldn't say, have a vote, most people think that machines can think or most can't, ergo they do or they don't think. Or by intuition, like I feel that it thinks or that it doesn't think. Because that really puts out of the, sort of, when we have intuition, right, we're always framing it through a human lens. And so it doesn't really become so much concerned with the question, so much as it is with what we think. In this paper, he popularizes the imitation game. which is now known as the Turing test. Interesting to look at how he actually frames it in this original paper, because it is kind of different from how most people understand it. He also speculates some theoretical implementations of the imitation game. So how might we build a machine to actually do the imitation game, which is interesting to think about given the time that he's writing at, which is before a lot of machine learning happens. Then this is pretty cool. He identifies and rebuts 9 different arguments from a large variety of backgrounds against the possibility of thinking machines. And this is like, he's writing this at a time where most people think that machines can't think. So this is pretty cool to think about as well. Most principally, he puts forward an intellectual framework to measure and think about intelligence in a way that's abstracted away from the human, which is also interesting. And also, lastly, he's also very presciently identifies learning as key to AI, which is not something that was identified around that time. And we know now that that's sort of been key to modern machine intelligence. Okay, let's talk about the imitation game. Most people probably already know this, but we have an interrogator, this black box over here, and we have a human and a machine, kind of. So the purpose of the interrogator is to determine which one of these is the machine and which one is the human, right? So the interrogator can interact with the human or the machine only through the medium of voice, or well, text, right? So there are huge walls separating all 3 of the digits in the scene. Turing originally articulated this in terms of gender, which is interesting. So he said one of them is a man and the other one is a woman. And you put the machine in one place and you try to determine from that as well. That's sort of been removed in the modern conception of the imitation game. Also to note, practically speaking, Turing actually suggested a variant of the game where the 2 agents, the human and the machine, only give binary yes/no answers to questions posed by the interrogator. The reason why I did that was because at his time, it was hard to imagine a machine that could actually give natural language responses. And so,
550.
in this case, it's sort of a binary yes or no answer. But still, the point is that if you have a machine that's able to imitate a human well, even by giving well-posed binary answers to well-posed interrogator questions, that satisfies the prerequisite for intelligence or thinking. Okay, so why the imitation game at all? Firstly, Turing makes a big point of separating the physical from the intellectual in terms of capacities. So he says that by having all these walls, right, that separate each of the entities, thinking becomes judged on the basis of intellectual activity rather than necessarily physical processes. So like if I give you like a robot, right, and I say, is that thing thinking? You might look at it and say, okay, it doesn't have arms, feet, doesn't look like me. Therefore, I don't think it thinks, it doesn't look like me. So his whole thing is that by separating the physical from the intellectual, we can more truly measure the intelligence of the system, which is a novel thought at that time. Here's a question to think about that's sort of engaging in like Cartesian mind-body dualism, where we can sort of sever the mind from the body. We should think about if that's really possible. So like one thing that the emergent language group has thought about a lot is, well, what does it mean to have language and to think about things, right? Like if I say the token apple, right? Well, modern natural language models can have a bunch of associations between like apple and let's say red, fruit, et cetera, but it hasn't felt an apple, it hasn't tasted an apple, it hasn't thrown an apple, it hasn't dropped an apple on its head, right? And so does it really know what the apple is if it hasn't physically experienced it? Well, that's a question to think about. To what extent is the mind separated from the body with respect to intelligence? Turing says you can separate them. So most people can get this by imitating humans. We just have machines that are optimized and judged on their ability to act like us, which most people would say are thinking beings, rather than sort of abstracting those to arbitrary skills of intelligence, like how fast can you calculate arithmetic, right? Which was something that was, which was where thinking machines were going towards. People just said, if you can do arithmetic faster, then you're a more thinking machine. Turing's key intellectual contribution here in the sort of history of how we measure intelligence of machines is what I call model agnosticism. So this is the idea that when we actually measure the state of the system, all that matters is the behaviors, like the input, the output. How does the input map to the output? It doesn't matter the internals of the system. It doesn't matter how that mapping happens. As long as that behavior is intellectually similar to, let's say, a human, right? And we're saying that it is thinking, because how can we have a machine that demonstrates human thinking behavior without actually being thought to have been thinking at all? I will note that general philosophy of thought has been favorable in the scope of history. If we think about how humans have thought about other races or species of animals throughout history, right? Anti-model agnosticism has always been on the wrong side of history, right? Because people do is they look at the internals of the system, right? So they say, okay, there's no way that this race, right, can be thinking about things like we do, or there's no way that this animal can be thinking about things like we do, and so therefore, they're sort of slashed out, right? And so in the scope of history, we have moved towards model agnosticism, which is interesting to think about. And so maybe that becomes applied not only to biological phenomena like animals or humans, but also to machines as well, which is what Turing is poking at here. Or, well, we'll talk about that. So he speculates a little bit about digital computers. This part is very speculative, but he's sort of poking at the objection that, okay, well, computers can't really do that. This is too difficult of a task. So he's saying, okay, like with modern inventions in digital computers, maybe we can. So his statement is that digital computers can do anything that human computers can do. He's talking about human computers as people who are hired to be basically today's calculators. And he's saying that when we have humans that are thinking, our thoughts are really just complicated hierarchies of digital operations. And so, if you just aggregate a bunch of them together, then you have thought, voila, right? Kind of dubious, but that's what he says. Also, he says, digital computers are electrical. Their nervous system is electrical. Put two and two together and can't think, something like that. So he, this is the formal Turing test question, which is not really can machines think, which Turing actually sort of doesn't like because I think that it's sort of a sensationalized representation of the question. It's kind of long, but you can just say he's adding a lot of stuff about technicality, implementation, feasibility, and interchangeability. So that's sort of the ultimate Turing test. Okay, he gives a lot of arguments and rebuttals. Here are 9 rebuttals that he identifies have been made against the possibility of thinking machines. I'm not going to go over all of them, but are there any that some people might be interested in looking more at? Which ones that maybe seem more compelling? Yeah.
You know what? I actually don't understand any words in mathematics. What is Gödel's theorem?
Okay, so that is so. Okay, so Gödel's theorem Gödel's theorem is basically saying that math itself is not really complete. Like it can't be used to do anything. That's not really a universal tool. So Gödel's theorem and a bunch of other theoretical work in mathematics on discrete state machines, so DSMs, those are like the computational devices or theoretical computational devices of Turing's time. So he's basically saying that people say that there are mathematical restrictions on what those sort of machines can do. Therefore, it can't really be intelligent because it's restricted by those domains. And so what Turing is saying is that, okay, those are theoretical restrictions on current discrete state machines, but the machines will evolve and abstract to the point where those become no longer relevant, which is what has been true, right? Which is we technically still at a very low state operate on quasi discrete state machines, but it's become so abstracted that we can now build like complicated neural networks that do stuff. Does that make sense?
Can you specify exactly? I guess Gödel's theorem. I thought it was a genuine but it just seems to say like mathematics is quote unquote incomplete.
Oh, it is a theorem.
Is it real? What does that mean?
No, it's like it's really complicated, but what you can do is kind of express math itself, like all of math mathematically, and then you can start reasoning about math, and then you can make proofs that certain proofs are impossible.
It means you can't prove everything.
Essentially what it means is that math will never be complete. So in math, there's these things called axioms, which are things that we just take to be true. Like, parallel lines never cross is an axiom. And Gödel's theorem says that basically no matter how many we add, there are things that we will never be able to prove or know.
How is that relevant to?
Okay, so basically the idea is that a lot of these thinking machines are based on mathematics, right? And mathematical principles. And Gödel's theorem is kind of saying that those are not universal tools. And the idea is that in order to have intelligence, you kind of have to have those like universals like tools. If that makes sense. It's kind of abstract. You talk more about it in his paper.
It's saying that because these discrete state machines are mathematical in nature, they can't think because of looking at.
That's the rebuttal that he identifies, but that's the argument that he identifies. But his rebuttal is that those are restrictions of low-level states, which we can abstract away, which is what has been done with modern compute.
Okay.
Yes.
What does it mean by nervous system is not?
Yes. So in that argument, he is talking about the right. So he's basically saying that our current tools for machines are discrete state machines, right? Which is what he had in his talk. The nervous system is not discrete. It's like more quasi-continuous. And so the objection that he's, identifying there is that, okay, nervous system not discrete, discrete state machines discrete. How can you move each other? And he is basically saying that doesn't matter because if it passes the Turing test, then it passes the Turing test. So a lot of these objections, as you can probably see, are premised upon the internals of the machine, right? So he's saying that if you just take input and output, then that's all that really matters. Like imitation game type stuff. Okay, key idea from Turing: a computer would deserve to be called intelligent if it could deceive a human into believing that it was human. Right? That's the key idea of the imitation game. If you were to kind of summarize that. Okay, last slide on Turing. Turing at the very end does speculation, right? Which is very interesting. He talks about the largest obstacle of thinking machines as being a matter of programming or implementation, which is obviously true. Like you can't do much with DSMs. He speculates that you need 1.25 gigabytes
6 o'clock.
to satisfactorily play an imitation game, which a little bit off. Kind of optimistic. Right.
I mean, yeah, like I could be convinced that you could make, like, if you had perfect, like the perfect algorithm, that the model itself could be compressed to that size, maybe.
Right, but you also lose performance with compression.
Yeah, like it's within a couple orders of magnitude of something that's like maybe sensible.
Right, a couple others.
I think it's a little more than that.
Like,
Right.
Like how many gigabytes?
like
It's like a couple hundred, I think.
I think way more than that.
More than a couple hundred?
And that was 2 terabytes.
Yeah.
Well, how do you measure that though?
That's huge. Yeah.
Oh, so the efforts are like 2 terabytes. 2 terabytes?
Yeah, like in one piece, yeah, a single cell has more information. Okay.
Yeah, I think the key point is that Turing underestimated the amount of abstraction needed from the discrete state machine level in order to actually reach that level. Also, very important, he suggests the idea of instead of simulating the adult mind, simulate a child's mind and then simulate the evolution or education of that mind into an adult brain. This is very different from the dominant thinking about AI at that time, which is more symbolic. It's saying, okay, we have an expert system. Let's just try to model that system instead of starting from like a blank slate and then moving forward. So this is philosophically known as the tabula rasa approach or the blank slate approach. And that is the philosophical foundation of all modern machine learning. The idea is that you start from a blank slate, right? And then from there, through the process of learning, you gather knowledge. And that is what all of modern machine learning and statistical learning has been based off. We have random initialization, which Turing actually proposes, which is pretty cool, as the tabula rasa, the blank slate. And then from there, we move forward. He proposes a few activities or tasks to start measuring intelligent machines on. He says chess is a very difficult and abstract problem to solve. Sure. And then also language, which is cool because language, yeah, it really hasn't fully mastered yet either. Last quote, that's interesting. We can only see a short distance ahead, but we see plenty that needs to be done. Okay, that is Turing's paper. On to the next one. So John McCarthy was a professor at Northeastern University, I forgot which one. He coined the term artificial intelligence, and he did a lot of the work in early AI. So this paper, ascribing mental qualities to machines, tries to do a few things. First of all, his idea is that we can legitimately ascribe mental qualities like beliefs, intentions, and wants. I think I spelled intentions wrong, whatever, to machines. That is a pretty unpopular idea at the time. How can you suggest that machines have beliefs and intentions and wants? Those are human things, right? He proposes a few definitional tools to help us actually do that legitimately and safely. Also, most importantly to us, he gives some examples of mental qualities that might be ascribable, as well as some examples of machines with mental qualities. This paper is pretty, I think Shane will like this paper because it kind of supports the trees intelligence thing, but whatever. So I'll try to get, this will be pretty short because it's not that relevant, the paper to us, but his idea about, okay, when is it legitimate to actually start ascribing mental qualities? It's legitimate if it expresses the same information about the machine as it does about a person. So that's not a trivial thing to think about. So why ascribe things at all, right? It helps us to understand the machine's structure, right? Its temporal behavior. What is the machine's past, present, and therefore future? And how can we go about fixing it or repairing, right? So if we're able to express the same information about a person as it does about a machine, and that allows us to do all of these things, then it is legitimate. McCarthy notes, it is important to separate mental qualities from motivational structures. So motivational structures are the structures that underline or propel or propagate or support the mental quality itself. So if you think about like feeling, right? When you think about feeling, the mental quality of feeling, you probably associate that with a lot of its motivational structures, like feeling sad or crying or watching a sad movie or riding on a lonely bus at night.
Why are we sad?
Or getting a puppy, right? And maybe the puppy dies. So why describe mental qualities at all, right? We want to describe the machine and its state. However, to a certain point, right, when we start climbing up the level of the hierarchy of abstraction, right, we get to a point where it's no longer efficient to describe those sort of things at low level terms. Like we actually need the language of mental qualities to describe machines that demonstrate higher level system organization and the epistemology of those sort of systems. So we already see a little bit of that climbing of the abstraction ladder there. Computers, right? We're not going about describing what computers do in binary or assembly, right? We've already built up some level of abstraction with like, when you code, you talk about if loops, while loop, conditionals, while loops, functions, that kind of things. Those are already one level of abstraction. McCarthy is saying, okay, if we go one level further towards the point where it's demonstrating sort of intelligent properties or system level aggregate properties, that really we need the language of mental qualities in order to actually talk about those things efficiently. That is a pretty utilitarian understanding of mental qualities. It's saying that mental qualities are essentially references to information that we use to manipulate to understand systems and things broadly. This is both similar and different from Turing in several different ways. First of all, he is not purely model agnostic. He is using mental qualities to understand the internals of a system, right? So how is actually making decisions or processing things? He's using the language of mental qualities to actually think about those sorts of things. So he cares about the internals of the system. However, he is similar to Turing in the sense that he intellectually moves away from what I call greedy anthropocentrism. Greedy anthropocentrism is the common enemy to everything in this presentation. It's the idea that intelligence and other sort of mental properties and qualities are for humans only for us, no machines, machines not smart, machine done, right? That's greedy anthropocentrism. We sort of keep all those qualities for ourselves. And so intellectually he's moving away from that by abstracting mental qualities to machines. Okay, here are some examples of the language of mental qualities. These are things that you might say about a human, right? And that were only said about humans at McCarthy's time, basically, and how you might apply those to machines as well. And so he has some related mental qualities. He's saying that you can apply all of these to machines. So consciousness is a complicated one, and we can decide if we agree with that or not. But he's saying that you can say a machine is conscious if you can look at its internal behavior and it expresses the same information about a human as it does about the machine, right? So when we say someone is conscious, right? Well, if I say, hey, you're conscious, right? maybe I'm trying to express that Alec knows himself, or he has a concept of a self, right? And so if in the system, there is a term for the self that is used in a meaningful way in reference to the self, then McCarthy says, you can say that it's conscious, legitimate, like philosophically that is sound, which is his framework for thinking about that. And you have other stuff like intentions, free will, and that kind of thing. It gives some examples of systems that do have mental qualities. He says thermostats have mental qualities, and that they have beliefs, right, that they acquire through observation, that they update and in turn act to adjust the state of the system. So, maybe that's true. He also says, like, for instance, self-reproducing cellular autonomy. I think that's how you pronounce it. For instance, like Conway's Game of Life, right? So he says that we can say that those have mental qualities. Why? It doesn't matter if they, necessarily do or don't. They do if it expresses the same information about a human as it does about that thing. So again, sort of a utilitarian understanding of that sort of thing. Does that make sense? It's kind of abstract how he's using the concept of mental qualities. Okay, nice. So we are done with basically around half of the presentation. Here is a nice little break from Sigmovic. It is titled "Using Deep CNNs to Prove That I Look Better Than Tom Cruise and Shah Rukh Khan Combined." That is an Indian actor, I believe. Yes, it is by this guy from Carnegie Mellon University, published very recently. This is groundbreaking work. Okay, we start out with thinking about a new way to look at CNNs, right? You've heard about image to vec, right? That's just an autoencoder. You have an image, you map it into a vector. The vector gets mapped back out to an image, used for basically almost all things image related. Well, introducing image to float. So image to float is the same thing, except you just map it to a single float value, right?
610.
Map it to a single float value. And so now he is going to use image to float to prove that he is better looking than Tom Cruise and Shah Rukh Khan combined. How? We start out by encoding both of the faces into float values, right? So Shah Rukh Khan is 0.5834, Tom Cruise is negative 3.1162. Then you linearly interpolate between them, right? So you have negative 2.5628. You're combining Tom Cruise and Shah Rukh Khan, okay? Then you decode that and you get Shah Rukh Khan and Tom Cruise combined. Handsome guy, right?
That's surprising.
Right. Okay, so now the author is basically trying to ask, so he recruited some participants, right? Because you have to evaluate this. So he's saying, okay, 4 participants, right? Am I better looking than Tom Cruise and Shah Rukh Khan combined? 3 biased participants said that he wasn't. They were excluded because they were biased. And the one that said that the author paper was better looking was included. Ergo, we have 100% support for the hypothesis. So the author paper is better looking than Shah Rukh Khan and Tom Cruise combined. It is pretty impressive.
This is like funny and all, but I'm actually shocked. Like, I'm still shocked, like, the fact that you can reconstruct that. Oh, yeah. Wait, that's a joke. You can get that. Because I don't know how to get, like, I need this data for total value, right? That's
My best guess is that it was only trained from that data set of faces.
Yeah.
So it's basically generated an average face with like one feature controlling the perturbations in some directions.
Yeah.
Yeah.
So, why not do like a interpolation of like a larger lighting space in this case?
Right.
That's the joke.
The joke is that, yeah.
I was wondering, is there like a magnitude on that single value?
What do you
What's the
mean?
magnitude of that value? Yeah, but like what's the maximum?
Right. That's determined. That's up to interpretation by the decoder, basically. So like they work together to determine the scale. Usually it's centered around like.
Feel free to just run it and just like plug in increasingly bigger numbers.
Yeah,
Right,
and
yeah.
I would imagine it just like explodes eventually.
Yeah, both the number and the face.
Right. I mean, the thing is, if you actually increase the latent space and you use things like variational autoencoders, you can get a very realistic interpolation between the two faces.
Yeah,
But the thing is, like, those are pretty good looking people. And so when you interpolate between them, They'll probably also get something that's pretty good looking. The point is that when you have a float, right, you damage all the information, and so you get that guy.
It is possible because floats have, like 64 bits.
Right,
So
but-
if you were smart enough, you could, in theory, like figure out how to leverage all those bits.
So it would have to be a very discrete mechanism. You'd have to sort of bin them very properly, which would be kind of hard to do.
More stats like that.
Like I mean, let's say we're using 32 float bits as this tradition. You just have, let's say, 3-bit floats, and just have it be a quantized model that uses, or let's just say 4-bit floats.
Yeah.
Yeah, and have it be a quantized model for, like, quantized not in the sense of the language version, but just use smaller floats. You could fit like 8 small floats into one regular float.
Right.
And then they have very few possible values.
How many dimensions are there to space, right? It's like lots of different. There's a few dimensions.
You probably get it to work, but using all these
information.
Yes. Maybe another symbolic thing. Okay. Should we take a break if people want? That was kind of dense, and this is more dense. So, do you want a break? Like 5 minutes? 3 minutes? We are. Yeah, we're on time. It's nice. I like having that. It just keeps me on track, you know? It's like you're scrolling through, social media or something. It's 11,
5, 10.
yeah. Okay, break, no break? Small break? Okay. Yes, and also an AI guy. I did not talk a lot about that, but he actually gives some mathematical, well, like logic-based implementations for how to talk about mental qualities. Yeah, he was a big guy in like symbolic logic and symbolic AI. Coined the term AI, right? So.
I think coin that term, it's like words too.
Right,
Yeah.
but you get your internal stamp on it.
Doing anything fun this week?
That's fun.
Yeah, my neuroscience has to be midterms.
Jenna helping out your friend with the stat stuff.
I have a lot of
No,
midterms.
she is somewhere else.
Right.
On the ground.
Related.
You have any midterm stuff?
No, I did my logic return.
Your logic?
Oh,
yeah. What was, how was it?
I'm looking forward to next week.
Yeah.
Watching.
Watching what?
Hamilton.
Oh, really?
Yeah.
They had in like, where?
What do you mean? That's okay.
Right, but like, at like a play or something?
Yeah, I don't know exactly.
That's cool, that sounds fun.
Yeah.
I guess gonna like road trip over there.
We're gonna fly.
How much are tickets?
I don't know.
I lost 4 points because I forgot to. I did only 2 things wrong. I didn't introduce new variables arbitrary.
That's fun.
Yeah.
And you friends?
I guess I won't be able to on Friday.
I proved it.
Okay.
But it's so annoying because I basically just you take the predicator and I plug
When
it
you're
in.
leaving?
That's wrong.
When are you
For some
leaving?
reason, if you
Friday,
take
right,
it,
right,
it's
right,
true,
yeah.
you're like, $3 thrill, and then you can't assume that.
That's fine. That's fine.
Then you have to like flip everything.
Also, the
alternative is
very legislature did not work at all.
It didn't?
It's not really, no.
Which method was that?
See, it's like, yeah,
That was the one I had.
Oh, right.
I started.
Yeah. It's kind of weird it did that. It's kind of weird it did that. Is it just too extreme?
I don't know, I'm like.
Is can you upload your code somehow?
Yeah, I'll put on the GitHub.
Okay. Right, okay. Sounds good.
But it's weird because it gets to the point where it just is outputting lines single every time.
Right.
And still doing shit. Like after
Okay.
if it's that line symbol, then it should.
Right, it should be doing. Yeah, yeah.
I don't know.
It's supposed to take you 30 minutes, but I used the entire.
I wouldn't be surprised. Yeah.
That's weird.
I'll have to think some more about it. And let's just have a keyboard.
No one's gonna use it. It's so hard to type on.
Imagine playing games.
This week? No. No, pretty normal week. I have a math midterm next week.
Yeah, I think I have math midterm as well. Good.
What?
What?
Okay. So those are fun. That's fun.
Yeah, they're fun.
Yeah. I like the math midterm. I like the math midterm. They're short. They're like 5 questions. Yeah, for us.
Yeah.
All the time.
I'm not French. I've been missing more classes too.
I mean, if you do well, advanced stuff.
Yeah.
Nice, yeah. Are you filling it in well?
Yeah.
You are? Okay, that's good.
6:20.
Okay. Computer has summoned us. Okay, buzzer was also summoned us. All right. Hey guys, you want to start again? Okay, cool. We are now going to get into what I think might be a little bit more interesting to y'all. It's a little bit less philosophical, a little bit more concrete, which hopefully will be interesting and very relevant. So please make sure, it gives good fodder to talk with Chollet about. Okay, so this is 2017 on the measure of intelligence, published very recently. Okay, here is generally the contributions that he makes. First of all, makes a big statement. We need a concrete measure of intelligence to actually make progress towards intelligent AI. We can't just sort of talk and gesticulate abstractly about what intelligence is. We need to actually have a number or a set of numbers to understand and move towards intelligent artificial intelligence. He suggests that there are 2 primary conceptions of intelligence hitherto in cognitive science, and that both are wrong. He suggests a new one. He talks about measuring skill as a really poor way to actually measure intelligence. So skill not equal to intelligence, but we have always been measuring skill, so far in AI, which is a bad path to go out. He proposes a set of guidelines for how we might go about a general artificial intelligence. And I think interestingly proposes an actual equation to understand and measure the intelligence of a system, which we will laboriously work up towards. And then lastly, he also proposes the abstraction and reasoning corpus as a benchmark task for actually building human-like artificial intelligence. Okay, part 1, context and history. So this is sort of what's happened before, what Chollet finds lacking in that, and what he will move forward. First thing that he talks about is we need explicit intelligent metrics. So far, he talks about AI as being brittle. So that means that it's engineered or optimized for very specific tasks. If you ask it to do anything outside of that specific task, it sort of breaks down. He asks, why has AI gone in this direction? Well, his answer is that specific tasks are a lot easier to measure. And so when we have a very concrete metric, we can very easily move towards and optimize that metric and have advancements and so on and so forth until we get an AI that's just really good at optimizing that metric. To move towards general AI, therefore, we need explicit intelligence metrics. Okay, what intelligent metrics are there already, right? We have common sense definitions, right? So that's basically what we were working off of in the tree human debate, right? It's like, what do I think intelligence should be? What's intuitively intelligent to me? And then we have the Turing test and also some variants of the Turing test. Chollet says these are all not good. Why? Because the Turing test really, if you think about the Turing test, right? The interrogator has so much control over the intelligence of the, well, not control, but they have so much influence over the final determination of the intelligence of the machine, right? Because the interrogator is the one that's actually making the determinations. Intelligence gets tied to how much the interrogator knows. And so we've actually seen, as we've gone through time, right? We've always had machines that claim to pass the Turing test, right? Like you were able to fool people into thinking that you were a machine or a human. Well, as AI gets more advanced, we keep on seeing those claims that machines pass the Turing test, but we never really think that they're intelligent, right? Why? Well, one hypothesis is that, as we become more acquainted to non-human intelligences, that we're sort of better able to differentiate those two things. We kind of think of it as like a GAN setup, right? Like you have the generator trying to fool the discriminator. We get better over time at discriminating. And so really the Turing test isn't really very concrete or explicit at all. Okay, so far hitherto there have been, Chollet identifies two key understandings of intelligence. The first one is intelligence as being really good at task-specific skill, and the other as emphasizing generality and adaptation. And so these broadly map to two understandings in cognitive science. The first understanding, so task-specific skill, right, is that the mind is basically an arrangement of quasi-static, specialized mechanisms that are sort of arranged together and fine-tuned throughout evolution to just be really good at that task. So like, you think about our eyes, right? How do our eyes evolve to just look at things really well? That just becomes a really specialized component of our body. Or like different parts of the brain that specialize in certain areas or tasks that get assembled together to coordinate coordinate to do certain things. So here's some proponents of this perspective, right? So evolutionary psychology is all for this idea of us developing various compartmentalized task-specific skills and adaptations that get put together to form our intelligence. Also Darwin, right? Big evolution guy, thinking about how do mechanisms evolve and become fine-tuned to solve certain tasks and to sort of climb the ladder in terms of natural selection. As well as, Minsky, a big, symbolic AI guy, and also generally just pre-1980s, symbolic type AI, big proponent of this sort of specialized system of intelligence. Second understanding is that the mind is a general purpose learning algorithm that turns somewhat arbitrary experience into knowledge and skills. This is the idea about generality and adaptation. So this is a tabula rasa approach, right, to how learning should work. And so, first and foremost, Turing, right, so he talks about that. In the first paper, we talked about computing machinery and intelligence, tabula rasa type things. Friedberg, John McCarthy, also a proponent of this sort of thinking. Papert, another, old AI guy. And then in general, this post-1980s AI, which has been more obsessed with learning and tabula rasa type approaches towards, growing intelligence, have really emphasized this sort of understanding. And also, even before that, we have thinkers like Aristotle, Locke, and Rousseau that have also been sort of building upon this idea of what constitutes intelligence or intelligent behavior. Okay, Chollet says that both views of human intelligence are flawed, or they don't capture the full picture. And so throughout the paper, he's going to work towards a synergy between the two that he thinks more truly reflects human intelligence or what intelligence should be. Okay, today's step back now. Let's talk about the success of metrics, right? So why has deep learning developed the way it has towards task-specific skills? Well, he says that if you look at every basically key development in deep learning, the primary thing that's been behind that is almost always benchmark data sets and standardized metrics. So you look at all these different competitions and systematic ways of measuring, comparing, and ranking different types of approaches, right? These have been behind a lot of the key developments in deep learning that we have now. So like the ImageNet challenge, right? Early 2010s competition, that so many key computer vision architectures came out of that, out of people trying to measure and beat each other on that challenge, right? Also like glue, which is big in natural language processing. Cool thing, UW NLP is like a big player in maintaining glue. You have the WMT for machine translation, the DARPA Grand Challenge for autonomous driving. Like you have all these challenges and metrics and benchmarks and data sets, and they give people a way to compare, rank, measure, and optimize for whatever the metric is measuring. So I think metrics have been key to the development of modern deep learning. Okay, what is the problem with narrow AI metrics or metrics for task-specific skills? Well, it propagates the AI effect, right? Which is what y'all might have heard of it. These two are good descriptions of what the AI effect is. The idea is basically whenever AI does something new, that we say, oh, but that's not really intelligent. And so, intelligence always becomes the next level of what machines haven't done yet. We just keep on shifting that and shifting that and shifting that. So those are two good descriptions from certain thinkers. Chollet makes this assertion: there is no single task X such that a skill in X demonstrates intelligence, right? You can't just be really good at a skill and have that really be intelligent. So if you look at so this guy over here, Reed, just an example. If I beat the world's chess champion, I'd be regarded as highly bright, right? But when a machine beats the world's chess champion, as it did many decades ago, we don't really think that that machine is really intelligent. Why? Because narrow skills are impressive in the context of generality, right? So when we have a human actually, get really good at chess, we say, okay, that goodness in chess is impressive because they're a human and they can also do all sorts of other things, right? Like cognitive reasoning, thinking, feeling, etc. A machine literally built to do that one thing is not really considered intelligent. And so that's a key thing to think about in terms of why is just measuring skills not really a good way to move forward in terms of actually developing intelligent systems. Okay, so now how might we consider generalization, right? So the concept of generalization originates from a statistical context, right? So you have all these data points, right? And basically, how do you connect them? How well does the curve interpolate between those curves? How well does it generalize? Now in deep learning, the concept has a significantly renewed significance because we want to think about how neural networks can interpolate or generalize across these huge, very high dimensional spaces that we can mention. And so we can consider two types of generalization. We have system-centric and developer-aware. System-centric, you can think of it as sort of interpolation. So can it generalize to what the system has seen? Like if we give the system this kind of stuff, can it generalize within that? Developer-aware generalization is, okay, now can it see things beyond the system that the developer hasn't really anticipated either? So you can think of that as like extrapolation almost. Is that distinction clear to people? Yeah, okay. All right, so what has currently been tested in terms of actually evaluating bot models? Well, one idea is that we have the concept of reinforcement learning, right? In which the actual feedback plane, if that makes sense, is a lot more continuous or fine-grained than sort of a static supervised data set. The question that we should ask is, to what extent are reinforcement learning models being evaluated on their training data? So if you train a reinforcement learning model in its environment, right? We don't technically have like a training set, test set, but it's being exposed to so much of the environment through exploration that when we put it in the exploration, actually in that environment to see actually how it does, well, it's really only perceiving slight perturbations or trivial modifications of what it's already been programmed to see. Also, we have like multitask benchmarks where basically we try to say, okay, not just one skill, how does this machine do across several different skills? Well, Chollet is saying all the methods currently, they don't assess robustness or really quantify how models generalize. And so they can be solved with basically cheats, right? Like we build a model to do this specific type of thing. It happens to work for this specific thing, but doesn't really generalize across the broad scope of intellectual problems. So if you're interested in how these cheats are generated or how we arrive at cheats, I recommend reading this paper. Under specification, it presents challenges for credibility in modern machine learning. That paper talks all about why machine learning models may happen to converge to solutions that they shouldn't converge to and don't work out of the environment within which they were built. Yes.
So I'm trying to understand the difference between interpolation and extrapolation better because.
Yes.
Like, to what extent is it something that you have not seen before? Like, you know, if you are able to make some prediction on something, then you have to, yeah, you are classifying it in terms of something that you have seen before. So like you're making a connection to something you've seen before.
Right. So the canonical example is, let's say that I have a regression, right? And let's say this is like x equals, and just say it's and I just train like a regression, let's say to do this thing, right? Of course, the regression extends, let's say, right?
Yeah.
So if I ask you just to say, okay, I give you a new point within this range, can you do it well? Okay, it does well. That would be like system-centric generalization. It does what the system sees. Then we give it like x equals theta plus, let's say, 10, right? And ask it to give a reasonable prediction for that type of thing. So it's out of what the system has already seen. And we say, okay, you also have to do well on that in order to demonstrate developer-aware generalization. Of course, regression fails this because it's, it just does interpolation, as do arguably a lot of modern deep neural networks. This is happening in very high dimensional space, of course.
Regression probably does that.
It does.
Yeah. Well, it's like hypothetically, if you actually are modeling, if you're linear regression, it's actually the model of this, the underlying distribution.
Right, yeah.
But it's probably.
But the thing is, it has consistent memory. And of course, this is just like a theoretical example.
Yeah.
And actually, the ARC data set is a really good example of extrapolation, what truly being able to transfer skills might look like. It's about learning to learn rather than just learning the relationships. Learning how to learn relationships so that you can learn new relationships without being trained to have learned them. Okay, so right now we kind of fall short, Chollet argues. We have this idea of surpassing humans in skill, right? Versus developing broad abilities, which is what Chollet is more interested in. So if you think about like this idea of surpassing humans in skill, right? So skill-centric development. These are things like moonshots, right? We hear that a lot in tech entrepreneurship now, which is, okay, we're going to shoot for the moon and beyond, right? Go for these huge things. It's often associated with a lot of sensational advertising. You can think about like AlphaGo and AlphaZero, right? So that was really sensationally advertised. You know, Go, world's hardest game, robot beats human, right? Also like Dota 2, which plays a video game. I'm not very familiar with video games. Super sexy stuff, right? Oh, AI is beating humans and all that kind of thing. Versus when we think about like broad abilities, right? So like it's like learning to learn. I talked about before. That's a really challenging problem. Right now, all we do is really just learn. We don't really learn to learn. How to acquire new skills, right? So not just being really good at doing this one skill, but acquiring new skills. So you have to be general and flexible in order to do those things. Those are kind of less sexy and harder to pursue than this sort of ideal of surpassing humans in skill, which is what most of AI has been doing. And Chollet argues is not the right way to go towards general AI. Okay, we made our way to past part one. Now part two, this is where Chollet actually makes his movement towards his formation of what intelligence is like, as well as his equation for intelligence. Okay, we already talked about this. We cannot just evaluate skill, right? So we remember what Turing said, right? He speculated at the end of his paper, chess is a really good abstract task to try and build intelligent thinking machines on. We all know that you can actually build a pretty good machine to play chess without it actually being very smart. Why? Because, well, chess can be a very abstract task, right? When humans play it, we play it as an abstract task generally. However, it can also be solved without abstraction, right? It's like you just do a minimax or tree search and you can pretty trivially solve chess. So if we want to actually think about evaluating the intelligence of a system, we have to think about the difficulty of abstraction or the possibilities of actually solving that solution. When we think about learning, right, we should think about what are we really learning right now? If we're thinking about modern machine learning, we're basically learning to hard code knowledge from data. So instead of being sort of symbolic and just directly hard coding knowledge, we're just saying, okay, you'll learn how to hard code knowledge. But the knowledge is still hard coded within there. And so therefore, this is Chollet's words, you can like buy performance on the task without actually doing any without, okay, I did a stutter with that word, I don't know why. You can't do the G word. Right. So in order to actually evaluate the model, we have to rigorously control the priors, experiences, and G-word difficulty without actual evaluation methods, right? Within evaluation methods, which you'll see each of these components represented in the actual equation for intelligence that Chollet proposes. Okay, here's something interesting. Chollet says intelligence has to be anthropocentric, okay? So this idea of a universal intelligence is a scam. Human intelligence is both adaptive or general, as well as specialized, right? So if you think about our various tasks, right, or the things that we can do, well, yeah, we have a lot of very specialized functions, right? Like if I put someone in this room on Venus, right, would they do very well? Probably not. So we have like very task-specific adaptations, both in our biology, our physical body, and in our mind, right? But we can also be very good at acquiring new sorts of tasks within the scope of specialization, if that makes sense. So this is where we're sort of fusing both of those original conceptions of intelligence, both the tabula rasa approach as well as the task-specific approach.
Is this the thing where he brings up the something theorem that says we can't, like, the other paper?
Yes.
Sorry. I'll get back to you.
Okay, cool. So Chollet says, I think he puts it nicely here, an anthropocentric frame of reference is not only legitimate because necessary. So we have to benchmark progress against human intelligence. So it's important to recognize that this anthropocentrism is not the greedy anthropocentrism I talked about before. It's not saying that those properties or intelligence is restricted to humans only, but it's sort of a realistic or necessary anthropocentrism that represents that when humans build AI, we're always going to have to compare it in reference to the human mode of thinking and intelligence. Okay, we're almost there. Almost there to the equation. Almost there to starting the equation. Okay, let's talk quickly about priors also, okay? So priors are where intelligence begins from, and that's really important to think about. So a lot of work in developmental psychology throughout the years, decades, have shown that most skills and knowledge that we have are acquired rather than innate. We don't like start off as babies and just have like the seeds for ideas that are already going to grow up and bloom into a mature human. Most of our skills and knowledge are acquired via interaction through with our environment, and that what's in that seed is not necessarily the knowledge itself or the roots of the knowledge itself, but the learning algorithm that develops those. And so cognition is shaped with those priors that are the source of how we actually acquire new skills. And so Chollet identifies some key human cognitive priors, right? It's like we have low-level priors in our sensorimotor space. So like teeth chatter or other sort of things that are at a low level that you don't really control, but just happen. Like those are the priors of your system. We have meta learning priors, right? So like causality, like I hit the table, it makes a sound. It makes a sound because I hit the table. So priors about how we actually learn and make links between information about the system and the world. And also knowledge priors. So these are things like objectness, right? Like if I look at the water bottle, right? Where does the water bottle start and where does the water bottle end and the table start, right? Or like, what if I, moved it there, right? Is it still the same water bottle, etc.? So what are properties of objects that we can identify and isolate? Also Euclidean spaces, right? Like I can pinch Jaegor's head. I know Jaegor's head is not that long, because I have priors about Euclidean spaces in the world that I occupy, etc. Right? So Chollet is saying knowledge priors, we have to especially control those because those are what we're evaluating when we're actually building intelligent systems. Okay, a recap before we dive into starting our climb of the intelligence equation. we have a few key principles that we should sort of recap before we start. So intelligence, first of all, lies in adaptability and generality, right? Rather than just skill itself. We can't just keep on pumping the skill metric higher and higher and not expect to go anywhere in terms of working towards general AI. Imagine intelligence has to control for priors and also quantify the strength of generalization or adaptability, right? So as we saw before, like chess, right? Chess can be solved through many ways. We have to actually look at the difficulty of solving that problem in a way that requires adaptability or keyword. General AI has to be benchmarked against human metric, against human intelligence, or be anthropocentric in nature somehow. And again, should I suggest that there really is no meaningful concept of a universal intelligence for us to pursue. Okay, here is a text version of a text synopsis of the equation that will be useful to refer to back later. The intelligence of a system is a measure of its skill acquisition efficiency over a scope of tasks with respect to priors, experience, and generalization difficulty. Okay, the key thing to focus on now is skill acquisition efficiency, right? So this is the key concept that he's talking about in relation to intelligence, right? So if you're intelligent, you're able to acquire skills in a very efficient way, right? So what is skill acquisition? It is the conversion of experience into skills. So he's saying basically that I am more intelligent if I can look at less information and still get more skills out of that, if that makes sense. And of course, we have to look at that process of skill acquisition efficiency, taking into account, what priors you already start with, what experience you encounter throughout, as well as how difficult it is to actually perform generalization in that problem. Yes.
So if we always benchmark against human intelligence, can we start passive?
Yes, depending on the task, right? And so actually for the fifth part, I'll talk about the ARC challenge. And that's a task that you can actually try to teach.
It's actually really intuitive.
It is, right?
Yeah.
But it's interesting because it's hard to formulate this yourself, but once you think about it, it makes sense. I feel like skill acquisition efficiency, conversion of experience into skills is a very good way to actually think about intelligence, which is not really captured by other methods. Okay, you guys ready for it? Okay, so the big question that we're trying to answer is, in changing the word, what is this LaTeX garbage heap? So this is one of Chollet's equations for intelligence. We'll just look at this one because that's all we have time for. But this is, Chollet's saying, okay, we need metrics, right? We need concrete intelligent metrics to actually look at the intelligence of a system. So he's not just talking the talk, he's walking the walk, right? So here is one of his equations for the intelligence of a system that we can actually try to concretely optimize for. Okay, in order to understand this equation, we're gonna have to go through a lot of notation. Let's start out with the key components of this system, right? So we have an intelligence system, we have a task, and we have a skill program. The intelligence system generates skill programs. These are like candidate models or like agents, right? And the agent interacts with the task. So, it gets a situation from the task and it provides a response back and forth, back and forth. And so the task is able to say, okay, this agent did X, it did so well, or did not do very well. And it gives feedback back to the intelligence system in order to generate better skill programs. And also we have, a score at the end which just says, okay, how good did the intelligence system do in generating skill programs overall? So if you think about a neural network, right, and how a neural network maps to this idea of intelligence system. The neural network is not the intelligence system. Backpropagation is the intelligence system. Feed forward is the skill program, and the data set is the task. So the task is like the data set, right? Let's just say we're doing supervised learning. It's just like, let's say, here's an image of a dog or a cat. Here's a label dog or cat. Here are like thousands of them. So now the situation, right, is the input image, right? The skill program is the feed forward operation. You pass the feed forward operation with that specific set of weights and biases. So you pass the input image through that skill program, get a prediction, that's your response out, right? And then you give that feedback, so basically like the loss, right, back to the intelligence system, which is the update mechanism. And then the update mechanism basically updates the weights again and you generate this new skill program, which is just a feed-forward operation with slightly different weights. And so you iterate over that over and over again. So this is actually a sort of very broad way to think about algorithms and intelligent systems in general, which does not rely upon just deep learning. You can have it with other frameworks as well.
I'm just confused how, could you put it in terms of like a standard neural network and just make sure
Yeah.
you understand like the whole idea of making more generalizable intelligence, like idea that you can just create out the scale. How does this help? Because now you just see that the task is just a data set. And you're not really actually making it out with more than one skill programming.
Right. So when I was talking about neural networks, I was just giving one example of how one intelligent system might map onto this model of intelligent systems. So in that space, you're right, right? We have a really specific task. But as you will see, we can have a lot different types of tasks, which require you to have many different skills. In standard supervised learning, our task is just one skill, which is why we have sort of narrow AI. But this is a general framework for thinking about intelligent models. Yeah. Does that make sense?
And also, this is score. What is the score based on?
Score is just like the overall performance of the intelligence system aggregated across skill programs on the task.
The average performance of all skill programs.
Kind of, yeah. Just like it's not involved in the actual updates and learning. Okay, let's start out with some of the atomics of our notation. Climbing up the node. So theta t, that is the sufficient skill threshold. That's like, if we had to put a number on it, and this is going to be subjective as Chollet acknowledges, what is, how much skill do we have to reach in order to say that we've solved a problem, right? Omega t, that is the value of achieving a sufficient skill level at some task t, right? So once we reach that, how good did we do, or how good should we do
650.
by reaching that task? C is a curriculum. So a curriculum is sort of an abstract idea. A curriculum is basically a sequence of interactions between a task and an intelligent system during training, right? So that process of situation, response, feedback, generation, like this loop over here, that is the curriculum basically. Like, what are the sequences in the process of learning that need to happen in order to get you to a certain place? We have like optimal curriculum. So this is the curriculum that that gets the intelligent system to a point where it generates the skill program with the highest skill. And we have sufficient curricula, which are curricula that basically get the intelligent system to a point where it generates any skill program that just reaches the sufficient skill threshold. So do these three make sense? These are sort of the key atomics to understand.
What is T?
Sorry, T is task. So T is just a task.
What was omega again?
Omega is the value of achieving sufficient skill level at T.
What does that mean? The value?
So like, let's say chain, what's 1 + 1? Okay, I wouldn't give you very high reward for that. Okay, solve the P equals not P problem.
So I see. So
Right, yeah, yeah.
assigning arbitrary values to.
Right, it's somewhat arbitrary, but it is actually pretty arbitrary. But we can sort of say that certain tasks should be rewarded more than others. And that's a discount factor that will factor in that, yeah.
So like, let's put this in terms of like a neural network I you earlier.
Okay.
The skill threshold could be like an accuracy threshold.
Yeah.
And the value of achieving sufficient skill level could be like, do wait and miss critical, and then doing something to the other.
Right, right, and then maybe even higher for ImageNet, and then maybe higher for something more difficult. So these are like system level constants.
So they could, for like really abstract machines, it'd be harder to like pin down for like for a network. You could write it as it looks like.
Right, yeah, yeah.
You guys are using curriculum though. I get the optimal one almost, but what is that C? Is it like, what is the units of C?
Right, so C is, just think of that as like basically a list or collection of the history of the education or update of the intelligence system.
Yeah, I think it's exactly right.
Yeah,
Or
basically.
So you have the state action pair and you just kind of listed those.
Yeah, basically that.
Okay. But it's more to do with the training, right?
Right, well, they're both curricula. It's just the optimal curricula is a sequence of interactions that gets you towards generating a skill program that has the highest skill, whereas a sufficient curricula just gets you to a program that reaches the threshold. Yeah. Okay. Solution with respect to theta and t, that's the shortest solution to the task t that achieves the skill threshold theta. So implicitly we're thinking like that's like the best, the most comprehensive solution to that task. So we'll call that the system solution. That's basically like in the entire system, right? What is the best solution in the entire possibility of space?
So it's like, if there is a solution,
Right.
the solution.
Right, so like
even if we don't know it.
right, so I kind of think about it like, but like if you have like a training set, right, versus the entire data set, think of the system data set as like the solution across the entire data set. Whereas, sorry, I can choose. This one, the train solution, that is like the best solution that one can find just given the training data set, right? So the difference between these two, there's no difference except this one is a solution to be found just in the training set. This is just what can the model get given its information. This is what is the solution to the system, right? Irregardless of if the model can actually reach or not, given what it's doing trained on. Does that make sense? Makes sense? Okay. Chollet's equation relies on a lot of algorithmic complexity theory. So I will talk very vaguely and hand-wavily about what these two things are. But H of S, it is the algorithmic complexity of some string or program S. So that is like the length of the shortest program outputting that string on the universal Turing machine. Just think about that as like, if it's bigger, then it is more complicated, basically. And then we have H of S1 relative to S2. That is relative algorithmic complexity. Basically, how much relative complexity does S2 have about S1? So we can define that as the shortest program on a universal Turing machine that produces the string S1 when given S2, right? So if S2 is the same as S1, right, they have zero relative complexity because they're the same. You can just directly translate it out. But if they're very different, then we have to go sort of write longer programs to actually morph like one program into the other.
What is S exactly?
S is like a program basically. Like think of it as like the skill program generated by the intelligent solution. So that could be like weights, right? Like the weights in the neural network, kind of. This is the reason why using algorithmic complexity here is just to be very general about all sorts of possible programs that could be generated here.
Yeah, so on instance like reinforcement, if you go back to the slide with the boxes.
Yeah.
So it wouldn't necessarily have to be, so like it's something like a vision task. If I understand correctly, the intelligent system itself kind of has to be just background.
Yeah.
But in a reinforcement environment, you could consider it, or like, let's say in a human environment, like let's literally just like people doing this. To me, it makes more sense to think of it as the system, intelligent system, and the scope program are kind of the same, where it's just the intelligent system mutating itself, mutating its own state in response to feedback to act as a scope program that. So,
Yeah, I say that's fair.
I think it kind of makes sense to think about like that in reinforcement as well.
Right.
And because if we're going to be implementing, let's suppose we can implement reinforcement learning that ends up becoming intelligent and taking over the world. What we would need is like, unless we want to have a completely like different kind of system, a different to backdrop, like it produces programs, produces different sets of weights for different things.
Right.
Maybe that'd be cool, but that honestly seems like that'd be better to be included in the architecture itself. Secure seems equivalent to think about that.
I guess so. You could think of it that way. I guess the concept of an intelligent system is pretty broad too. Like if we just use like evolutionary strategies, right?
Yeah.
Well, each of the agents are the skill program, but evolution is the intelligent system.
Yeah.
If that makes sense.
So also kind of is more convenient for the computational complexity.
That is true. It is a lot more. Okay, so basically just think of this like, if it's bigger and more complicated, this one, if it's smaller, then two programs are in terms of complexity similar to each other. It's like a similarity measure.
So is that right? Relative complexity S2 has about S1.
Yes, so given given S2, we want to, oh yeah, I think it's the other way around. Wait, let's do S2, this. So it produces S1 given S2. So, well, no, it is the right order because we're trying to produce S1 given S2, right? So S2 is like the prior of the system. And we're saying how much information does S2 already have about S1 such that we can transform it into S1.
So it has all the information that given S2. Yes.
We can trivially transform it because they're, you know, all the stuff that's there is already there. Okay, let's start building our atoms into molecules, right? So this is actually, okay, whatever. So this is a system-centric generalization. This is, I'll just read it out. The proportion of algorithmic complexity of the system solution explained by the shortest possible training time solution. So remember the system solution, right? So that is the solution to the entire system, right? Regardless of if the model actually finds it or not. This is the solution that the model can actually find within the training space. So it's basically saying, how hard is it to do this problem from a system-centric generalization difficulty perspective? So how much do we need to go to transform the training solution into the actual system solution? So if these two are very similar, right, then that is it's zero, right? Because the training solution and the actual system solution are basically the same. So our relative complexity is zero. Therefore, our difficulty is zero. So it's trivial to go from what we learned in training into the actual system itself. On the other hand, if our training solution, if we don't have that much, complexity about it relative to the system solution, so the actual system solution is overwhelmingly more complicated than the actual training solution, right? What it can get just out of training, then we have very high GD because it's hard to go from training out into the actual system. Does that make sense?
So
yeah,
just as we put like abstract terms, difficulty of forming in the real world given the training.
Yes. Yeah. All right. This is a variation. This is developer difficulty. The only difference is that we don't just take in the training solution. We also take in the initial state of the intelligent system. Again, this is sort of abstract. He has, if you want to dive into it, he defines these more comfortably in the paper itself. But this is basically, we also take into account the initial state of the system such that we're able to be more informed about what the system or the state can or can't do. Because training solution, right? This is what you could theoretically get in the entire training system. But how do we know if our model can actually get to that system or that state or that solution, right? That's why we also consider this. And so you can say, okay, can it even really reach that system or that solution at all? Okay, this is the prior of an intelligent system. This is how much information does it already have at the start. This is pretty intuitive, I think. So you have the algorithmic complexity of the system solution, right? So this is just how complicated is the system solution overall. Then you have, you subtract that from the relative complexity of the intelligence state relative to the system solution. So that second term is basically saying how much work is it to morph the initial state of the system, i.e. the priors or what it already knows, into the actual system solution. And so, like, if they're the same, if the model already starts out with an initial state that basically has all the complexity and information needed to get to the system solution, then this is zero, right? And so we have a very high level of priors. If this is very large, I mean the algorithm system and the actual system solution have a very large discrepancy, then this ends up being very small. Does that make sense?
What is IS?
Intelligence system.
Right. Like how do we compare it with forms of that?
He has the more specific stuff, but it's basically like a collection of states of the intelligence system.
So like parameters. Or something like that.
Basically, I can think of it as like, in terms of neural networks, because that's what we're familiar with, right? Think about like that as like the random, the first set of weights, basically. Think, okay, neural networks, right? The first set of weights, the optimal solution to the neural network, like the absolute hands up best one. And then you try to see how difficult is it to get from that initial random state, or that whatever initialization scheme you're using into that best system state. And that's you subtract that from the complexity of the solution state itself. And then you actually get the priors of the system itself.
When we like train, would that be the weights that it's been trained?
Sorry, what do you mean?
It's not on the slide. Like, train.
Yeah. So, so train is, so it's kind of complicated, but train is the theoretical optimal solution only given the training data set. System solution is the optimal solution for the entire world, the entire phenomena. Like if we want to measure like, ImageNet type things, right? Like the optimal thing to measure all cars, all trees, whatever other categories there are.
So as for linear regression, if we have just 2 data points, the best we can do is basically just put a line.
Right.
And that's probably how.
Right. Yeah. So it's all about what does it already have. So the proportion of algorithmic complexity of the shortest solution of the task of this field threshold data explained by the initial system state. Okay, we also have experience. So this is basically the amount of relevant and novel or new information received by the intelligence system at some state t. So this is basically looking at, okay, I have my current state of my intelligence system, for instance, like where it's at right now in terms of generating intelligent programs versus the optimal system solution to that state, as well as new data that we get. Right? So how relevant is that data to solving this? If the data is really relevant with respect to whatever state we're already in, then this will have a very low value, right? Because this explains the solution well. And we compared that with, okay, what if we did not have that data? And we just compared that with, how far do we need to go to actually get to the system solution? And that ends up being our experience. So if this is very high, right, because it's very hard to go from our current state to our, the best solution, then we have our data, right? And the introduction of that data makes this very small because now the distance to go from this to this is very small. Then we have experience as being very high, right? If the data is not that important, then this is like being very low. We don't accrue that much new and relevant information at each step. That makes sense to everyone?
So it's more experience you have, the closer you are to solution, super data set to.
Kind of, yeah, basically. It's just measuring how much closer basically does that new data bring you towards going from the current state to the system.
And this is just at one particular time step.
Yeah, just at one time step. Okay, so now we can just sum over all interactions or all time steps in a curriculum, right? A curriculum which is just basically a sequence of time steps. And we get overall experience measured over an entire curriculum. That's really intuitive, I feel like. Okay, we're almost there. I just have to add a few more molecular atomics, which are like higher level terms that are not really atomics. Okay, this thing, that is the space of curricula from an intelligent system that generate a sufficient scale solution for a task, right? So just think of that as like, if I'm thinking about a neural network, right? And I just look like, here's my state, right? I think about, okay, let's say that all of these models, right? All these 5 models are models that achieve my subjective understanding of what it means to pass that task. I.e., it reaches the theta t, it reaches the sufficient skill threshold. Then what I want to do is I want to trace each of these curricula, right? So like, let's say that, maybe we decide I'll get it in this direction, so on and so forth. So I record each of the paths or the curricula, the interactions between the system state, the intelligence state, and the task, right? And I store all of those, and that becomes my curve with respect to the task and the sufficient skill threshold. It's just a collection of all of the paths or education curricula that can get the intelligence state to generating a sufficient skill program. And then PFC, that's the probability of a given curricula C. So let's say that just in our stochastic update process, that let's say that like it's very likely that the first step that is that we're going to go down this path, right? And then maybe this path and so on and so forth. So if we were to run, let's say, this experiment like 20 million times, what's the probability that we end up in following one of these curricular paths? Does it make sense? Okay. Let's take on the beast. So hopefully now you understand some more of these things, right? Let's start on the very inside from this term, which is really doing all the grunt work. So we have our generalization difficulty, right? And we have our priors plus our experience, right? So note that priors plus experience, that's the total system exposure to information about the problem, right? So we have priors, we have initial information about what the system already knows. Then we have experience, which is accumulated over time steps through interactions with the system. And that together forms our total exposure to information about the system. And then we have GD, right? So that's recall from before. Basically, how hard is it to solve this problem by being trained on the training data, but also doing really well on the overall system solution. So if you see the GD is really high, right? So it's super hard to actually do this problem, but the information that we get from the system is very small. Then this term overall is very large, right? On the other hand, if the GD is very small, but our information is very large, right? Then this value decreases. Okay, everyone good on that part? That term?
I was writing stuff down. I feel like you said some important stuff, but if you quickly go over it.
Yeah, for sure. So we have our GD, our difficulty of the problem, right? Yeah. So if the problem is super high, but we don't get that much information about the problem itself, then this value is very high. We can think of that as like value for that, or like difficulty, right? On the other hand, if the GD is very low, right, but the information that we get out of the system is a lot, then it becomes like a less valuable problem.
So valuable problems are harder to solve.
Right. And if you can quantify the difficulty to solve a problem from a learning perspective with this term, basically.
Give us a second.
Yeah, sure. Does this make sense to everyone else?
Very high T means we know a lot about the problem based on prior.
Sorry, high what?
We know a lot about the problem based on prior.
Yes. Yeah. So basically, how much information does the model have from the very get-go? So like, if we had some sort of like really smart neural network starting scheme that wasn't just random, right? Then actually like random initialization probably has higher information value than just L0s, right? Maybe. So then that might be already like one step higher. So that'd be a higher prior than that.
Are you sure it doesn't? Are you sure that it means like initial starting state, not maybe the point at which you are predicting, like how much knowledge you have at the point at which for example, GPT-3, like, well, maybe they randomized the network at the beginning, but it makes any predictions,
Right. Yeah. So
Well, that comes from the experience, right?
That's my question.
the prize is mainly a question about actually learning, right? But it's the process of learning that gets you to a state where you actually start predicting things. So if you look at the formula, right, it's looking at the initial state. It's saying throughout the process of learning, right, how much does that have to go?
And this analysis of an intelligence system, and in the case of just neural networks, that'd be backdrop. So it'd be an analysis of backdrop with random initialization learns this well, whereas backdrop with random initialization to multiply every weight by 4, subtracts 5, and if they're greater than 0, they're set to -8. That's probably going to do a little worse. So that is it's probably going to take longer, potentially reach a worse solution depending on certain properties of the platform. So in this case, the intelligence system is the entire training algorithm itself on data sets.
It's the learning algorithm, basically.
Um,
And also candidate proposal mechanism.
Yeah, and how you initialize the state is part of its of itself, sort of.
Right.
It is that's what it is at the start. And
Or, sorry, go ahead, actually.
yeah, if you want to evaluate an intelligent system, kind of just have to take that back-based approach.
Right. Or think about like pre-training, right? So you know, transfer learning, right? So we train the model first on some task, some generic task, then we retrain it on the more specific task. The priors there are a lot higher because you already have the base skills needed to solve the specific task. So that's already even one level higher than just like random random weights. Yeah. Right. Okay. Moving on. We want to also weight this by the probability that we actually encounter each curricula, right? So if we encounter some curricula more often, we should probably weight the value of actually, getting to that state a lot more than like a very rare curriculum. And then we just sum that across all the curricula in the space, right? All the curricula in the space that end up leading to a sufficient skill program. Okay, then we have this thing, so omega t times theta t. That is the subjective value of achieving sufficient skill in the task T. So this is our sufficient skill threshold, right? And then this is the value of reaching that threshold. So if the sufficient skill threshold is very high, right? So it's really hard to actually get to that's sufficient threshold. And also our value of getting to that place is very high. Multiply those together, and so we have very high value of actually getting to that sufficient skill. On the other hand, if it's like an easy problem, so low beta t, and also we don't really care that much about what it solves, right? Multiply them together and you have a small importance. Then you just average that across different tasks. And I didn't really talk about this, but we have this idea of a scope, right? A scope is basically a set, like the entire space of tasks that you have to solve in order to actually sort of to evaluate a law. So like maybe we don't just want to see if this intelligent system. So again, the intelligent system here is not any one model. It's not any one set of weights. It's the learning algorithm. So like back propagation is one intelligent system. Evolutionary algorithms is another intelligent system. And we want to see, okay, well, how will this backprop do, for instance, on SciFar, right? And then language, and then MNIST, and then Boston housing data set, right? So we're looking at all sorts of different tasks and evaluating the intelligence system, this method of update and learning, rather than the model in and of itself produced by the system, which is like the skill program. So you average all of this across all the tasks within the same scope. That's important. Tasks have to be comparable to one another. My examples are not very comparable, actually. So like a scope might be like all image recognition tasks of a similar difficulty somewhere. And put that all together, and you have the intelligence of the system with respect to that system, the sufficient skill threshold, and the scope of problems. Yeah.
Okay, so just to clarify, I just want to give like examples so I can see where it falls apart or stays together.
Yeah.
So say that you said image recognition is a scope, right?
Mhm.
And our let's say our intelligence system would be. Would you say intelligence system would also deal with like choosing convolution versus like a feed forward, for example?
So okay, so you're talking okay. So I think that's part of it. So an intelligence system has to, it both defines how the candidates are structured or defined, right?
Yeah.
So my earbuds are falling out. But also the update algorithm, right? Like that propagation as well. And so when we're thinking about this intelligent system, right? We're thinking about the abstract idea of putting convolutions and then putting feed-forward networks, stacking them together and then getting like a good output, right? So it's tied to the general idea rather than a specific model architecture or set of weights itself.
Okay, so all right. I guess the rest of my question is kind of like that. So okay. So if we're talking about image recognition in general, you could say like just take two data sets as two tasks in this.
Right. Yeah. Yeah.
We should call them tasks, because we're talking about a single task.
It can be tasks, yeah.
Oh,
They follow the same scope.
Oh, so the scope is image recognition, and task-based society, like, image net versus.
Yeah.
So, on the right with the GD, monitor over there.
Yeah.
For MNIST, the GD value, what is that actually called?
Generalization difficulty.
The generalization would be relatively low.
Yes.
And because we have so much data, that denominator would be very high. Or,
Okay,
it could be very-
so you're right in that the GD is relatively low, because the difficulty from going, like, if the model is really well on the training data set, it's probably going to do really well on a validation data set, because there's no difficulty in really crossing the boundary from a training to put from like develop from system aware to developer aware, right? But the priors over here, so training, like that's experience, right? So that's how much information you can get out of the system, which is a lot, right? Because they're literally digits, you can get a lot of information out of that. So, yeah. The priors will probably not be that much for known numbers because they're random and data right?
And then, for something like ImageNet, it would be like generalization difficulty, I guess, a bit higher, because they show an ImageNet, but then say, go to a picture of a cow on that side.
Right,
I
yeah,
think
yeah,
that's the task.
right.
In that sense, so it'd be very high. Priors would be the same, because that's still a number, and with the experience, because it is compared to the scope of the task, which is not as anything, for example.
Right, yeah,
You don't have much, so that'd be a very, very high, that fraction would be very, very high. And then, let's say, for example, that you were in a world where there's only digits like 3 cows or something like that.
right, yeah.
Then even though that fraction is huge for the ImageNet like classification,
Yeah, sure.
that in that bracket space would be pretty low, because the chance of like actually finding that would be very small. Just in this type of world. Is that what would that P sub C is for?
720.
That's about right. So with curricula, right, we're thinking about learning pathways, right? So like throughout just think about yourself when you're growing up and learning things, going through the education, chain, right? There are many different paths that you could have taken that would have all gotten you to a sufficient place, right? We're looking at, well, what's the probability that you fall down that specific, that specific history of updating? So what you said is it's kind of correct. I think your idea about the world is more applicable to looking at tasks across scopes. I will say that, okay, so few-shot learning is one problem in image recognition where we give you like 5 examples per class. And we say, okay, generalize, right? So the priors are super low here. And the experience is also really low because we only have like 5 samples. But the difficulty is very high. So few-shot learning is one example of a task where you get rewarded very high if you have this. And you think about the task as this entire thing, right? Because this pertains to a particular curriculum.
I say, I said it the curriculum is. So is this even calculatable, because it is assuming that you can like branch off?
Right. So it's an equation, right? So if you know the values, then you can calculate it. Of course, the thing is, how do you find the values?
Yeah.
Well, Chollet has more in-depth stuff, which I'm not going to talk about.
How do you end up that? Is that like, because a curriculum is essentially like we're talking about its trajectory, a set of just like things that happen. But it seems like if your data sets is more randomness in that stuff.
Okay, so curricula is the how the model evolves, right, over time. And so we have things like we have stochastic update algorithms, right, and we also have random init. So those are all modes of randomness that can help us say we go down this path with a certain probability.
And like you don't necessarily need like some local minimum, right? In this case, you need like a set of things that you do to become consistent or
right. Yeah. So just the sequence of interactions.
Okay, so it's not like a local minimum, because I was kind of
Oh yeah.
And then this element of curriculum is interesting.
Which is like for each C in the set of curricula that satisfy that solution. We consider all. Yeah.
Okay.
Okay, I'm gonna try to rush through the rest of it because I really want to show the arc data set, which is really interesting. Well, let's really quickly look at some properties of the equation, right? And what that tells us about the nature of intelligence. I talked a little bit about high conversion rate from experience to skill, right? So I think this is a pretty good graph, right? We have a limited amount of space, right? But this intelligent system is more intelligent than this one because you're able to get a broader, operational area of skill than just in this place over here. Okay, intelligence is tied to scope, right? You have to say this applies to a certain range of tasks. Skill is a property of the output of the model rather than the intrinsic model itself. Intelligence, you have to learn and adapt, right? So think about the experience accumulation, right? So you want to accumulate a lot of experience very quickly a lot of skill from the experience. Also, you can't just interpolate, you can't just do curve fitting over here, because then how are you going to extend to other domains? And also, intelligence is tied to the optimization of the curriculum, so actually the process of learning itself. I'll skip that. Okay, I briefly want to show the I spelled that wrong. The abstraction and reasoning corpus challenge. This is Chollet's suggestion for, a grand challenge that we should work towards getting AIs to solve. And it's pretty interesting and pretty difficult. So those are some of the goals. Pretty much similar stuff to what we've talked about before. Okay, so in the ARC dataset, there are 400 tasks in the training dataset. There are 600 tasks in the evaluation set. Each task is a problem, right? Like it's itself a task in the scope, right? Each task is unique, right? So there are 1,000 different tasks, which means that there's no overlap between the tasks in the training dataset and the task in the validation dataset. So the tasks that's in here are completely new. What it has to learn are not the tasks in the training set, but how to learn how to do the tasks. Each example within a task, right? So each task has a bunch of examples. Each example is an input and an output grid. The model has to produce an output grid entirely by itself that answers the question. And we'll see some examples later. And the model gets binary feedback. Either its answer was correct or was incorrect. Okay, here is one task, one of the 1,000 tasks. This is a symmetry task. So you look at this input, the model gets this input, and it has to produce this output. So it's given 3 examples, a small number of examples per task, right? Like few shot learning style. It's given example 1, example 2, example 3. This is the question, right? Fill in the grid over here, given what you've seen about rotational symmetry from these things. And so it has to look at these examples and generalize very easily and try to figure out what's in here. This is one task. Another task is denoising, right? So give it like maybe, so this is one example, right? And then you give it, a new one with some noise on it, and you ask it to denoise that one as well. This is a tricky one. Basically, this task is saying this task measures like objectness and movement. It's basically if I have the red shape and I move it towards the blue shape, right? When does it stop? This is one example, right? This is another example where we move it towards the blue shape. This is also a tricky one. This one is like basically the blue dots define like a direction, and it has to extrapolate out a path that bounces off the red wall and goes into another wall. And so it's given all these examples and it has to produce its own output, which in this case beyond back. So you can see that these are pretty tricky tasks. This is another one where it's kind of like Snake, right? Like you bounce off these walls in certain directions to reach the intended destination. This is an implicit counting game. It's basically, you have all these these shapes enclosed in 3x3 tasks, and you're basically counting which ones occur the most often, and reproducing that in the output grid. This one is a rotational symmetry problem, right? These are all tasks that humans can solve, but it's tricky, right? You have to sort of really be intelligent and be able to generalize very easily across problems to do that. You might be thinking, okay, this is a pretty hard problem, right? Like, I don't know a way to get an A doing that, and honestly, there hasn't been a lot of progress on this data set so far. But Chollet posted on Twitter some suggestions for how one might go about doing that. So I mean, his advice is just to start out solving it yourself in a programming language, just one task, and then figure out what is the thought process that you use to go about that, and try to generalize it from there. It's pretty difficult. All right, that is all. But
Not just that is all that will be.
that is all that will be. Yeah. So that was it. Something that I was thinking about was that I think the emergent language group might be able to take some sort of inspiration from like a subset of tasks here. Just because these are tasks that like they are abstract and we can take inspiration from that in terms of thinking about how language can play a role in successfully solving each problem. But I have kept you all here long enough thinking about root equations. So that is it.
Very insightful.